Hey guys, okay, sensory system today. Let's do this. All right, it's all set. Okay, so let's go ahead and fill this out. This one is a sensory receptor. So a sensory receptor is able to convert a signal from the environment, which is called the stimulus, into a nerve impulse. And then that signal is transmitted to the central nervous system so that it can be dealt with. Types of sensory receptors. So we have things called chemoreceptors. CHEMO is usually meaning it's something that's chemical based. Response to chemical substances, examples include taste and smell. We have photoreceptors, which respond to light energy, and this is going to be things like sight. Okay, then we have mechanoreceptors. Stimulated by forces and pressure, hearing, because the sound waves, when they hit the inner part of the ear, and also touch. And then finally we have thermoreceptors, which are stimulated by temperature change, also something we notice in touch, our skin. Okay, I'm going to fill these out real quick. Just going to go down my key here. Okay, all right. Vocabulary you will need to know. Okay, so let's go ahead and talk about the eye here for a minute. We have some diagrams you can look at that kind of shows what happens to the lens as the eye is trying to focus on things that are close versus things that are far, okay? So the lens is going to focus images on a part of the eye called the retina. To make this image of the lens happen, there are both ciliary muscles and suspensory ligaments that are involved, okay? And those will either flatten the lens out or curve it, okay, for vision. So for distance objects, the ciliary muscle is relaxed. Okay, so as the ciliary muscle relaxes, the suspensory ligaments flex. Okay. And tighten, if you will. And this is what's going to flatten the lens. The ciliary muscle and the suspensory ligament have kind of an inverse relationship. So if one is relaxing, then the other one isn't, and vice versa, okay? So to see something distant, sorry, I got my hair caught in my pen. To see something distant, we need to have the lens flatten out, okay? And to do that, ciliary muscle relaxes, the suspensory ligament is gonna flex or tighten. And then the opposite is gonna happen when we're looking at something that's up close. The ciliary muscle is going to flex or I guess we could say contract. And our suspensory ligament is going to relax. And as it relaxes, this allows the lens to become rounded. Okay. So those are the kind of mechanical parts of the eye that are functioning to help us adjust. Question of the day: why do my parents have to hold something so far away from their face to see it clearly? I was going to make a comment about assuming parents can't see, but okay. What happens is the lens, as we age, the lens of the eye tends to get harder, which means it doesn't change shape very well. So it has a hard time going from rounded to flat and flat to rounded, and so it needs usually some assistance in being able to do that. There are glasses that can do that, blended lenses, and then LASIK, corrective surgeries, things like that. Usually those types of surgeries let one eye be close and one eye be for distance. And it's kind of trippy from what I hear. I know some people that have had it done and the brain does adjust to it, but for a while they felt pretty tripped out. Okay. I mean, honestly, there's plenty of people that are not whatever you consider to be your parents' age that may wear glasses or contacts or have had corrective surgery, because there are some things genetically that can just cause some of those components of the eye to not function as well, including muscle or the ligament. That isn't about age. It can just be kind of a genetic issue. Okay. Photoreceptors. So here we're going to be talking about basically rods and cones. So rods are, well, these guys, if you look in this image here, they look more rod-shaped for sure. Rods contain something called rhodopsin, and cones, which not super pointy, but they're pointier, I guess. Cones contain something called photopsin, okay? And photopsin, it absorbs light, okay? So rods and cones each kind of have their own little task, if you will, and their strengths. Rods are sensitive to white light. They are what we use for night vision. And they're located throughout the retina, not just, well, I'll show you that in cones, but they're located throughout the retina. Throughout. You can spell. There's an activity you can do with this on peripheral vision. You put your hand over here by your ear, and then stare ahead, and then you just move your hand until you can see it. And so you can see it, you know, but it's going to be blurry, right? It's not till your hand comes around in front of your face that it focuses, that the image is able to focus. But the rods allow you to have peripheral vision to see something going on over here, okay? When it comes to the cones, much like printer cartridges, there are 3 types, or 3 colors, and that is red, green, and blue. Okay. Therefore, these cones are sensitive to color, not just white light. If you think about how things look at night to you versus how they look during the day, at night or during the day, you can see that a car is red. But if it's really dark at night, you're not under street lights, it may be a little hard to tell at first if that car is red, if it's black, if it's dark blue. And that's because at night, the cones aren't really working as like they do during the day, because they've got the white light that's coming from being absorbed by the rods instead. So instead of being located throughout the retina, like rods, these are located only at a part of the eye called the fovea. And the fovea is what lets us have that sharp vision, like what we expect when we're looking straight ahead at something, right? If you're focusing on something, your vision is sharper, whereas everything else kind of, again, in the periphery is a little fuzzier. Okay. So people that struggle with color blindness are either missing cones or their cones are defective. Okay. Then we have the blind spot. The blind spot is something caused where the optic nerve attached to the back of the eye, where it exits the retina, okay? So in this image right here, you can see it circled. The blind spot is here, okay? So in the back of the eye, the optic nerve, when it leaves, this part right here is the only place where we don't have any photoreceptors. So there's no rods or cones, which means that we're not able to take in any visual information that way. Okay, so the brain retrieves relevant information from your other eye to fill in the blanks, essentially. And then if you do this little blind spot test, it's interesting. And again, I'd encourage you to do it just because it kind of gives you a practical experience with what you're learning. But you find that your blind spot is different, obviously, just between the 2 eyes. Not different because you've got an optic nerve in the back here, one on the top here. The optic nerves are attached in the same place, but just the location of the eyes, the brain registers those blind spots differently. And so they kind of fill in the gap for each other, because what this eye can't see because of a blind spot, this eye can, and vice versa. So your brain merges those images to put it together. Okay, abnormalities of the eye. This picture always weirds me out. I don't know why. I feel like there's other pictures that could be used. This one weirds me out. But what you're looking at is a cataract. And a cataract has, obviously it's going to have issues as far as it makes your vision cloudy or can completely obscure your vision and can cause blindness because of this film that develops over the lens. And so the film is actually made up of proteins. Hang on, I gotta move this out of the way. okay? And again, this can cause blurred, fuzzy vision and blindness. And there are surgeries that can be done to remove cataracts. They have their own risk associated with them, like anything does. And sometimes they're effective and sometimes they're not. Then there's something called glaucoma. So glaucoma causes pressure to build up on the optic nerve, okay? What happens is the aqueous humor in the eye should be draining through little ducts in the eye, okay? And that relieves the pressure. It keeps the aqueous humor from building up. However, in glaucoma, those little ducts are blocked and it allows the pressure to build up then on the optic nerve, and that causes blindness. And pressure. Okay. Then we have something called astigmatisms, which is shown here in this little image. And astigmatism has cornea, your cornea is uneven, okay? So because of that, objects can't focus quite right because of this uneven surface of the cornea. So in order to correct for this, I'm trying to look to see what they were showing. There are ways to make lenses for glasses that have like a corresponding unevenness etched into the lens of the glass. And that uneven lens then allows the vision to be evened out and lets the person see clearly. Okay. Somebody that's nearsighted or myopic or have a hard time seeing distant objects, okay, because they can see things up close, have a hard time seeing things far away. That is caused, oddly enough, by the person's anatomy of the eye, the eyeball itself being too long. So if you look down here, this dotted line is like where the eye would ideally be, right? And then you can see that it's been elongated past that. And what happens is, in nearsightedness, it keeps the light rays from focusing on the part of the retina where they're supposed to. And so they focus early, okay? Let me undo this so you can see it, okay? So this is where it's supposed to focus, about where you'd expect a normal eye, quote unquote, to be. Notice that the eye itself is longer, which means the retina is actually farther back. And so it's focusing earlier than it should. And then there are corrective lenses that allow to see farther back by kind of altering where that light is going to focus. Okay. Farsighted is the opposite. The eyeball is too short. Okay, so if you look down here, again, if this is where a normal eye, quote unquote, should be, the light is going to focus beyond that point on the retina. Focuses behind it. Okay, and again, the shape of the lens used in glasses and in some contacts can make up for that, so that it makes the light focus on the person's actual retina versus where the retina would be in a normal eye. Okay. Right. That's it, you guys. That's all there is on this. It's kind of nice to have a shorter lecture, isn't it? So that's it. Bye.